On October 29, 2018, Lion Air Flight 610, a brand new Boeing 737 MAX 8, plunged into the Java Sea shortly after takeoff from Jakarta. All 189 passengers and crew perished. The world watched in horror, a tragic but seemingly isolated incident for a modern aircraft. Yet, just 5 months later, a chilling echo reverberated across the globe. March 10, 2019. Ethiopian Airlines Flight 302, another Boeing 737 MAX 8, crashed 6 minutes after departing Addis Ababa, killing all 157 people on board. 2 crashes, 2 brand new planes, eerily similar circumstances. The pattern was undeniable, and the implications were catastrophic for Boeing, for air travel, and for the global perception of aviation safety. Within days, countries around the world began unilaterally grounding the 737 MAX fleet, culminating in a global ban. This unprecedented action signaled a profound crisis of confidence. The immediate question was, what could possibly cause 2 such advanced aircraft to fail so catastrophically in such a short span? The answer, as it emerged, was not simple, and pointed to a confluence of factors deep within the aircraft's design and certification. For over a century, Boeing had been synonymous with aviation excellence, a titan of American industry. From the iconic B-17 Flying Fortress to the revolutionary 747 jumbo jet, Boeing planes were renowned for their reliability, safety, and engineering prowess. This reputation was built on meticulous design, rigorous testing, and a culture that prioritized safety above all else. But somewhere along the line, something shifted. The dawn of the 21st century brought fierce competition, primarily from European rival Airbus. Airbus introduced the A320neo, an updated, fuel-efficient single-aisle jet that quickly began to dominate the market. Boeing faced immense pressure to respond, and respond quickly, without the costly and time-consuming process of designing an entirely new aircraft from scratch. The 737, first introduced in 1967, was a workhorse, the most successful commercial aircraft in history. Its robust design had seen multiple iterations and upgrades over decades. To counter Airbus, Boeing opted for a familiar path: update the 737. The MAX variant promised significant fuel efficiency gains by incorporating larger, more advanced engines. However, these new, larger CFM LEAP 1B engines posed a significant engineering challenge. They couldn't simply be bolted onto the existing 737 wing without hitting the ground. Boeing's solution was to mount them further forward and higher up on the wing. This seemingly minor modification had a profound, unintended consequence on the aircraft's aerodynamic characteristics. With the engines positioned differently, during certain high angle of attack maneuvers, the aircraft exhibited an unwanted tendency for the nose to pitch up. This characteristic was known, but crucial to the 737 MAX certification was that it flew like previous 737 models. Pilots should not require extensive retraining or a new type rating, which would be a significant cost and time barrier for airlines. To counteract this pitching tendency and make the 737 MAX handle like its predecessors, Boeing introduced a new software system, the Maneuvering Characteristics Augmentation System, or MCAS. Its purpose was simple: automatically push the aircraft's nose down if it detected a high angle of attack, thereby preventing a stall and maintaining the familiar flight envelope. This was a critical piece of the puzzle. Crucially, MCAS was designed to operate based on data from only one of the aircraft's 2 angle of attack (AOA) sensors. If this single sensor malfunctioned and sent erroneous data, MCAS would activate, repeatedly pushing the nose down. This design choice, relying on a single data input for such a critical system, became a catastrophic Achilles heel. Perhaps even more alarming was that MCAS was not thoroughly explained to pilots. It was deemed a minor modification, a back-end system not requiring specific training or even prominent mention in the flight manual. Boeing assumed pilots would use standard emergency procedures for runaway trim if MCAS malfunctioned. But without knowing MCAS existed or how it behaved, pilots were flying blind. The decision to downplay MCAS and avoid extensive pilot training was deeply intertwined with market pressures. A new type rating for pilots would cost airlines millions and delay MAX deliveries, pushing customers towards Airbus. Boeing was under intense pressure to get the MAX certified in flying as quickly as possible, to maintain its competitive edge and market share. Adding another layer of complexity was the certification process itself. The Federal Aviation Administration, or FAA, traditionally the gold standard of aviation safety, had increasingly delegated parts of the certification process to Boeing employees through a program known as Organization Designation Authorization. This practice, while intended to streamline, led to concerns about oversight quality. The ODA program meant that Boeing employees, acting on behalf of the FAA, were reviewing and signing off on aspects of the aircraft's design. This created an inherent conflict of interest, company employees tasked with ensuring the safety of their own company's product. While not inherently problematic, the scope and scale of this delegation for the 737 MAX were later questioned, especially concerning MCAS. With this context, let's revisit Lion Air Flight 610. The flight data recorder revealed that a faulty angle of attack sensor began feeding incorrect data to the aircraft's systems. The MCAS software, receiving this erroneous input, repeatedly commanded the nose down. Despite the pilots' frantic efforts to pull up, they were fighting a system designed to override their commands. The pilots were caught in a loop, battling the automated system. Each time they corrected, MCAS would re-engage, pushing the nose down again. They lacked the critical knowledge that MCAS was even operating, let alone how to fully disable it effectively in that chaotic, high-stress environment. The plane, new and supposedly safe, became an unmanageable adversary. After the Lion Air crash, Boeing and the FAA issued advisories, but did not ground the fleet. They instructed airlines on how to handle an erroneous AOA input, effectively treating it as a training issue, not a fundamental design flaw. The emphasis was on existing emergency procedures, rather than acknowledging the unique and aggressive nature of MCAS. Just 5 months later, the tragic parallels became horrifyingly clear with Ethiopian Airlines Flight 302. Again, a faulty angle of attack sensor. Again, MCAS activated, repeatedly forcing the nose down. The pilots, despite their training, found themselves in an identical, unwinnable struggle against the aircraft's automation. This time, the world could not ignore the systemic failure. The second crash created an immediate uproar. Regulators globally, realizing the gravity of the situation, swiftly moved to ground the entire 737 MAX fleet. The data confirmed that the two accidents were virtually identical, exposing a critical design flaw rather than isolated incidents or pilot error. Boeing's reputation, built over a century, began to crumble. Intense investigations followed, led by various international bodies and domestic agencies. The focus quickly centered on MCAS. Investigators dissected flight data recorders, cockpit voice recorders, and interviewed engineers, pilots, and regulators. The complexity of modern aircraft, and the critical role of software, was laid bare for the world to see. Boeing immediately began working on a software update for MCAS. The primary changes included activating MCAS based on input from both AOA sensors, not just one, activating only once per event, and limiting the system's authority to prevent it from overwhelming pilot inputs. This fix was crucial to recertify the aircraft, but it took many months to develop and rigorously test. Alongside the software fix, Boeing also had to develop new training modules for pilots, explicitly detailing MCAS, its function, and how to respond to its malfunctions. This included simulator training, ensuring pilots gained hands-on experience in dealing with runaway trim scenarios exacerbated by MCAS. The era of no additional training needed was definitively over. The grounding of the 737 MAX came at an astronomical cost. Airlines faced flight cancellations, delivery delays, and financial penalties. Boeing itself incurred billions in losses, compensation to airlines, and a severely damaged reputation. The company saw its order book shrink, and its once dominant market position was seriously threatened by Airbus. Recertification was a painstaking process, stretching over 20 months. Global regulators, having lost faith in the initial FAA assessment, conducted independent reviews. Countries like Canada and the European Union conducted their own stringent evaluations, adding layers of scrutiny and requiring further modifications before allowing the MAX to fly again in their airspace. So, what was the real reason these planes crashed? It wasn't a single flaw, but a complex web of interconnected factors. An older airframe pushed to its limits, new engines creating aerodynamic challenges, an automated system, MCOS, designed to mask those challenges, its reliance on a single sensor, inadequate pilot training, and ultimately, a regulatory oversight system under pressure. The crashes brought harsh scrutiny to Boeing's corporate culture. Critics argued that a relentless focus on market share, cost-cutting, and speed had eroded its long-standing engineering-first, safety-first ethos. The pressure to compete with Airbus seemingly overshadowed the meticulous attention to detail that had defined Boeing for decades. In the aftermath, Boeing underwent significant internal restructuring, including leadership changes. They committed to greater transparency with regulators and airlines, and to re-emphasizing safety as their paramount priority. The company's future depends on regaining trust, not just through software fixes, but through a profound cultural shift that places engineering integrity back at its core. The FAA also faced intense criticism for its oversight of the 737 MAX. In response, the agency committed to comprehensive reforms of its aircraft certification process, particularly the Organization Designation Authorization Program. The aim is to strengthen independent oversight and ensure that safety decisions are never compromised by commercial pressures. The 737 MAX tragedy serves as a grim reminder that even in an age of advanced technology, fundamental engineering principles and rigorous oversight remain indispensable. It highlighted the dangers of relying too heavily on automation to compensate for design compromises, and the absolute necessity of transparent communication between manufacturers, regulators, and pilots. After nearly 2 years, the Boeing 737 MAX was gradually ungrounded, first in the US, then in other regions. With the software updates, extensive pilot training, and enhanced oversight, airlines slowly began to return the aircraft to service. The challenge now is to rebuild public trust, reassuring millions of travelers that the aircraft, once deemed unsafe, is now among the most scrutinized and thoroughly vetted planes in the sky. The story of the Boeing 737 MAX is a cautionary tale, demonstrating the immense pressures on modern industries to innovate quickly while maintaining uncompromising safety standards. It underscores that even the most advanced technology can harbor fatal flaws if not thoroughly understood, transparently communicated, and independently certified. The global aviation community learned profound lessons from the 737 MAX crashes. These lessons extend beyond Boeing and the FAA, influencing how aircraft are designed, how software is integrated, how pilots are trained, and how regulatory bodies exercise their critical oversight functions worldwide. The hope is that the high cost of these lessons will ultimately lead to a safer future for air travel.